accelerator being stuck on the car, that it should have let up, but it didn't. And so a mutation in oncogene makes cells grow when they shouldn't. Such oncogenes, of course, then become really important drug targets, because if you can develop a drug that blocks that effect, that unsticks the accelerator, then you've got something really useful. Tumor suppressor genes, on the other hand, are genes that normally serve as the brakes. They tell the cell to stop growing. And you have two copies of genes, so it's kind of like the front and the rear brakes. You could lose maybe your rear brakes and you would still stop, but if you've lost both copies of a tumor suppressor, and again, this is a common mechanism for malignancy, then the car crashes into the wall, in my simple analogy here. So much of science of cancer genomics over the course of the last several decades has been to try to develop a catalog of all of the oncogenes and tumor suppressors and a few other categories I won't go into of genes which, when misspelled, are capable of causing cancer. And what we've learned is that every cancer is different. And that's really important to know, which also means that probably every treatment should be individualized and not done in a one-size-fits-all approach if we knew enough about how to do that. Fortunately, it's getting easier to be able to acquire that information. I had the privilege, as you heard, of leading the Human Genome Project. It took us 13 years to read out that first complete human genome, and it cost about $400 million. But look to see what's happened to the cost of doing that kind of analysis. We're now down to the point where a genome of a cancer can be derived for a couple $1,000s, and that is continuing to fall. The technology for doing this, which used to involve sequencing machines as big as a phone booth, has now been miniaturized. I'm holding up a sequencing instrument here. It's about the size of a postage stamp, and it's getting even smaller as we go forward, and the cost is going to keep coming down. So this opened up a whole new window of cancer research to be able to look at lots and lots of cancers and say, what's going on there? Now, of course, you want to look at the cancer cells, and then you want to compare those to the normal cells of that same individual, which you can get from a blood sample. And then you can see what misspellings must have happened in that cancer cell to carry it from where it should be to where it is. And those become your targets. Those become the ways in which you're going to find the Achilles heel and go after that particular cancer. The Cancer Genome Atlas, founded a few years ago at NIH, a joint effort of the Cancer Institute and the Genome Institute, which I directed at the time, aimed to try to apply this technology on lots and lots of tumors from the most common types of cancer, and has built over the course of these 4 or 5 years quite an amazing public database of that information. But of course, what about pediatric cancers? If there was ever a place where we need to know that information to come up with new targets for those kinds of cancers that we currently don't have answers for, this is it. That's what the TARGET initiative is all about. Therapeutically applicable research to generate effective treatments is the acronym, but it's focused on pediatric cancers. You can see the map showing you where the samples were coming from. And that's not been the only area. This has already led, by the way, to a couple of clinical trials for new drugs. There's a project that's quite complementary to this, which is a collaboration between St. Jude's, who raised money to support this from private donations, and Washington University, which is one of our major genome sequencing centers. And they have now looked at some 600 childhood cancer cases, looking at the entire genome of the cancer, comparing that to the normal DNA of that individual. One of the areas that they've been looking at is low-grade gliomas, obviously an area of enormous importance given how difficult it has been for us to come up with answers. And they have identified in this kind of approach a variety of genetic alterations that suggest possible treatments, albeit with uncertainties and the need to do a lot more work to test those ideas. Another area that is worked on in the Genome Institute is a clinical sequencing effort supporting a consortium of researchers to develop methods, including at childhood cancer. Baylor College of Medicine has something called Basic 3 that is also focused in this area. You'll hear more, I'm sure, from Rhonda Pinho about other areas of this sort. The Baylor group basically saying if you do this, you find what you would call an actionable mutation, that is, something that suggests an individualized use of a drug therapy in 30 to 40% of cases that have failed standard therapy. That's what we're looking for, is to figure out how do you go from the one-size-fits-all approach, which is what we pretty much had to deal with, to something much more precise, much more personalized. And again, to be able to say we're on that path is exciting, but we have a ways to go. I have to be totally honest with you. Before I take your questions, I also want to point out another very exciting area of advances which have come along quite recently in just the last maybe 4 or 5 years. Although people have been working on cancer immunotherapy for decades, the promise of this has emerged in a much more exciting way in just the last few years. Science magazine every year goes through the advances of the year in all areas of science: physics, chemistry, mathematics, engineering, and life sciences, and they pick out one thing that is the breakthrough of the year. And last year, the thing they picked out was cancer immunotherapy. They have not actually done that very often for a clinical kind of advance, but this is sufficiently dramatic that they made that selection. So what are we talking about? This is basically how do you activate your own immune system if you have a cancer to actually go after those cancer cells, to unleash the power of the immune system to search and destroy those cells. And there are a variety of approaches that have been used in terms of various monoclonal antibodies, but I particularly want to tell you about something that is certainly high-tech, but which has some very dramatic early results, which is to genetically engineer your immune cells, to basically teach them to seek out and destroy the cancer cells, which means you have to know what you're doing here in terms of that educational step. The idea has been tested in a variety of ways. In neuroblastoma, a rare cancer of nerve cells, and certainly I'm sure there are people in this group whose children have been affected by this horrible condition and for which we still don't do nearly as well as we wish we would. And here, recently, in this article in the New England Journal of Medicine, an immunotherapy with an antibody which is directed against a particular molecule that occurs on the surface of neuroblastoma cells was tested in a phase 3 trial. While that intervention certainly did have a fair amount of toxicity, if you read this paper closely, a lot of these kids were reasonably sick as a result of the treatment while they were getting it, but actually the survival was substantially improved at a very high statistical level of confidence, and so this is now in the process of going into further late-stage development. But teaching T cells, one of the immune cell types, to go after a cancer is this a new strategy which you might have heard about, which has the acronym of CAR, but they're not talking about something that's used to be built in Detroit. I guess it still is. They're talking about chimeric antigen receptors. And the idea is that you create this molecule which is targeted specifically to that patient's cancer, and you put that into, by DNA transfer, T cells that you've derived from that patient. You allow those T cells to expand, and then you give them back. And these are, as one of patients I've talked to refers to them as her little ninja warriors who get into the system and go after the cancer cells. This is still early days, but there are certainly some very encouraging and even dramatic examples. One of those treated at the NIH by Crystal McCall, who I know spoke to you last year, is Phineas. Phineas's family is a powerful story to hear. Their first child developed acute myeloid leukemia and sadly was not saved by the treatments that were available. Second child was born and has done well, but their third child, Phineas, amazingly at age 4, developed acute lymphocytic leukemia, ALL. Now, as you know, ALL was standard therapy, generally responds, but sadly Phineas was in that subset that do not. And so after failure of chemotherapy, he became a candidate for this highly experimental chimeric antigen receptor approach. So his T cells were taken out. They were loaded up with this particular DNA construct that turned them into the ninja warriors. They were infused back into this 4-year-old boy. And over the course of time, his leukemia cells became less and less frequent, and they're now not possible to find. And if you saw Phineas on his first day of kindergarten, this is him. And we need lots more stories like that. And I'm sure those of you in this audience who have lost children wish that something like this had come along soon enough. And I do too. And those of you who have children who are struggling with cancer, again, we're certainly hoping that results of this sort from experimental therapies will happen as soon as possible. We definitely have reasons to be optimistic, but we also have reasons to be frustrated by the slowness of the effort. This is hard stuff. And it's also, unfortunately, at a time where we can't go as fast as we can because of the resource limitations. So I just want to finish by pointing out in sort of graphical terms why those of us at NIH are feeling pretty stressed about lost opportunities that we wish we could pursue. This graph shows you in the yellow line what has basically been our real dollars, so that's the budget for NIH but adjusted by inflation over the course of the time from 1990 to 2014. You can see that in 1998 there was that wonderful uptick. That was the doubling of the NIH budget, which many people fought for and which was achieved, but over a 5-year period. But then you can see what happened after that. A steady downward slide, so that we are now 23% below what we had in terms of purchasing power for research compared to 2003. Interesting, if you look at that dotted green line, if you go back to 1970 and simply look at the NIH budget and see how it averages out over time, it averages at about inflation plus 3.7%. That was sort of the trajectory we were on. Obviously, we did better than that for 5 years, but then we've done a lot worse than that ever since. If we just stayed on that trajectory, which I would argue would have been healthy for biomedical research, because stability matters a lot when you're trying to encourage investigators to take risks, we'd be $10 billion above where we are right now. Right now, if you're an investigator coming to NIH with your best and brightest idea, your chance of getting funded is the lowest in history. It's about 16%. Over the course of the last 50 years, it's been generally around 30%, which is still pretty tough. That means most people are getting a no, but now almost everybody's getting a no. And so scientists are spending more and more time writing grants instead of doing the research, getting rejected, getting discouraged. Recent survey said 18% of young scientists are now considering leaving the United States because it's so difficult to have your research go forward in this climate. Other countries, by the way, are being more supportive. But America is the place where so much of the talent and the promise resides. We shouldn't let that go to waste. What can we all do about this? Well, finally, I think we can raise our voices. And I know you all are, and I thank you for that, about the importance of research. Give us a hard time, push us, ask us why we're not making more progress. But I hope also all of our voices can be raised together to make a case here that the promise of medicine and medical research has never been greater, and yet the support for it is not making that possible at the speed and level that it could. So maybe all our voices can get together instead of having a soloist and have a real symphony here, because the music we need to make is not only important in a musical sense, it's important for the lives of children all over the country, all over the world. I give you my word that I will do everything I can to make that case. I will do everything I can when opportunities arise in childhood cancer research to make sure we are moving forward at the fastest pace that we can. And I really thank you for listening to these words, and I'd be glad to take some questions.